Hi everyone. Today what we're going to jump into is we're going to kind of change gears a little bit. And we've just spent a number of days dealing with an awful lot of graphical material. Today we're going to switch gears and jump into some more algebraic stuff. So you'll notice from the title today, we're going to get into, or back into in a way, solving trig equations. So what you're going to notice as you go through our lesson today is we're going to kind of work at some different paces. You're going to get an opportunity today to try some problems on your own, work ahead a little bit. We're going to go through very quickly at times, and then we're really going to pump the brakes in other spots. So don't be alarmed if kind of things seem a little jumpy today. Yeah, we're going to move at some different paces. So let's take a look at the instruction for problem 1. That should look very familiar for you. We are going to solve for theta, where theta is greater than or equal to 0, less than or equal to 2 pi. This looks like a problem that we dealt with quite a few lessons ago. Everybody should be good on problem A. So I want everyone to pause the video, jump through, solve a solution for A. Go. Okay, we should be back. And so as we work our way through, I would hope that most people would be good to put on a quick set of axes. Because my cos is positive, my adjacent is positive, which means I'm going to the right. You could then drop in your triangles because you have an adjacent side of 1 and a hypotenuse of 2. That is then going to say I have a big opposite side, so I have pi by 3 related acute angles. And therefore, your solution to that problem for theta would be pi by 3 in the first quadrant or 5 pi by 3 in the last. Now that that's come back, we should be good with that process and the fact that we have solved that trig equation many times. Now, what I want to do is just kind of extend into where we're going to go on this topic and where we go for the next couple lessons. Take a look at B. And what you'll notice is B actually looks an awful lot like A. That if you went through the process of isolating your trig ratio, which means let's get rid of that 1, and now let's divide out your 2, you'll notice that I actually gave you the same trig equation. So we don't need to finish off B. You guys can see how you would finish off B in your solution to A. But what we're going to start to address is situations like this, where it's not just like in A, where a trig ratio equals a value, but rather your trig ratio is not isolated. Maybe we have multiple trig ratios. All we're going to do today is to make our trig equations a little more complex, and then we'll talk about a couple issues that can arise when doing so. Okay, let's jump ahead and we'll keep moving with them. And so when you take a look at the equation given in C, you'll notice what I was talking about where I say our trig ratio is not isolated. When you take a peek, you'll notice that we have a sine theta and a sine theta. And my guess would be most people would be okay to be able to work through this problem, even with no guidance from me. Hopefully we can see that what we're going to look to do is isolate our trig ratio. And so on the left side of that equal sign, I could collect my sine thetas, and I'd have 2 of them. I have to get rid of the plus 2, and so that means I'm going to subtract 2, which gets me to that point. You then have the ability to isolate your trig ratio fully by dividing out that 2. And now that we come to sine theta equaling -1/2, we should be so comfortable to finish that off. Quick set of axes. Your sine is negative, so opposite is negative, so we are down. Opposite side, hypotenuse. Small opposite side means small related acute angle. And so therefore, your theta is going to be in the third quadrant, 7 pi by 6, or in the fourth quadrant, 11 pi by 6. And so what you're starting to see again is a progression like what we dealt with way back in grade 9 when we first learned how to solve linear equations. And so our key focus as we work our way through here is isolate your ratio, then solve for the angle. In that two-step process, we should be pretty automatic and pretty comfortable to be able to go through. So let's jump in and play with some more. So now when you take a look at problems D and E, you'll notice that we've jumped to some reciprocal ratios. I understand that that means we're probably going to tap the brakes a little bit, but it doesn't mean that we have to significantly change the way we solve. I want to walk through D in two different ways for us to be able to kind of work through. Okay, the first thing we can do is take D as exactly as it's written, and that's going to make us about as efficient as we could be. So what I mean by that is we could go straight and put on our set of axes because you notice your trig ratio is isolated. Okay, secant is the reciprocal of cos. So cos is adjacent. So my adjacent side being negative means my angle must be left. Now we could drop in, and here's the only thing we have to remember. Secant is the reciprocal of cos, and so cos is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Quite often we tend to think of that over 1. My hypotenuse over my adjacent. And by coming up with that value, you notice you have a small adjacent side, which means you have a big opposite side, and therefore we have our pi by 4. Notice that that would make that opposite side our 1s, and so we notice that we have our pi by 4 triangle. Okay, then in that instance, we could state that theta is going to be 3 pi by 4 in the third quadrant, or 5 pi by 4 in the third quadrant. Now, notice, I think that would be the most efficient route through. However, I understand that not everyone is as comfortable with reciprocal ratios as what they are with their primary. I could have a number of people that would say, well, I think I would prefer to replace that secant with 1 over cos. But notice by doing so, your trig ratio is not isolated. So we would have to multiply out that cos theta. Now, isolate your trig ratio. And what you'll notice, you're coming in on your diagram. Your cos is negative, therefore left, label your triangle, good to go. So for anyone who's looking at D and they're a little nervous about going through that process, no worries. You can change it back into your primary ratios. It just might make you a little less efficient. Okay, let's take a look at E for a second. So, couple things that we could work through is that we could go through and say, I want to be as efficient as I can be, and since my trig ratio is isolated, I can jump right into my rotation angle. I have cosecant. Cosecant is the reciprocal of sine. So if sine is negative, that means I am down. Now we can go through and we can create our triangles. Cosecant is hypotenuse over opposite. And so we could have our hypotenuse being 1.5 and our opposites being -1. For others, you're going to almost look at that and you're going to say, yeah, but like -1.5 is really -3/2. And perhaps you then label it as hypotenuse and opposite. It does not matter. In fact, you know you have a third option, which means you could replace your cosecant with 1 over sine. So we're going to work our way through, though, dealing with those blue rotation angles. Okay, the next thing that we should notice is that this is not a special angle. That we don't have a special triangle that has one of the shorter sides being 2 and a hypotenuse being 3. So what that means then is we're going to have to pull out our calculator and we're going to have to come up with an approximate solution. So first thing to notice, the restriction on theta in the original problem was given in radians. And therefore, your answer must be given in radians. So make sure your calculator is in radian mode. Second, we're going to have to push some buttons on it. And I don't know if we're overly comfortable dealing with reciprocal ratios on our calculator. And so as we've gone through and we've labeled that triangle, I'm going to have an awful lot of people that are going to come up with the measure of alpha, the related acute angle. And because of the way we've labeled those side lengths, they may come up with that alpha is the inverse sine of my opposite side over my hypotenuse. Or if we're using our green, then it is the inverse sine of my opposite over my hypotenuse. Again, just as a small notice, I did not use the negative when I did my inverse sine. That negative is what gave me the location of those arms. The number is what gives me the size of the angle. And so now as I deal with my inverse sine of my 1 divided by 1.5, again, remember that we need to be in radians, that we should come up with an approximate related acute angle of 0.73 rads. Now that we have the related acute angle, we can actually go through and solve for the principal angle. So finally, I'm getting through to solve for theta. I know then that theta is going to be pi plus my related acute angle to put me into the third quadrant, or it's going to be 2 pi minus the related acute angle to put me into the fourth quadrant. So we're going to go through, use our pi button to be as exact as we can be. And in the third quadrant, that's going to give us approximately 3.87 rads. And we'll round that to 2 decimal places as we get our approximates. Or 5.55 rads in the fourth quadrant. And there we go. So I really don't think that there's much more that I could put in at this time for us to be able to work through and deal with. We've gone through and we've dealt with finding exact values, we've dealt with reciprocal ratios, and we've dealt with approximate values. Okay, now it's time to kind of check where we're at with things. Okay, I would like everyone to pause the video and solve F on their own. Go to it. Okay, and we're back. And so if I was to start off the problem, I'm going to solve for my trig ratio in blue. And so maybe we're taking a look, and we might be positive coefficient people. We should get down to that point. Now, we take a look at that. Our trig ratio is isolated. It's time to deal with our rotation angles. Our cos is negative. Adjacent is negative. We're going to the left. We can drop in and deal with our cos. We notice that that is not a special angle, and so therefore we have to go through and use our calculator and get an approximate. Remember that I'm not using the negative. I'm just going through and using the positive to get my approximate value, and we should get approximately 1.23 rads. So we get to that point, and then we should be good. That we can go through then and say, therefore, theta in the second quadrant is pi minus my 1 0.23 rads, or in the third quadrant, it's 1. Wow. Plus that. And so, same thing, if we're going to go through and get some approximates, then we get approximately 3.26. I have no idea what that is. So we're going to get approximately 1.91 rads, or 4.37 rads. So hopefully we match up, and I would argue that if you were able to go through and deal with F, you're pretty solid with everything we've dealt with today. Okay, now we're going to change gears moving forward. So when I say change gears, I don't mean forget about everything we've dealt with, nor do I mean that what we've dealt with doesn't apply. What we're going to do is we're going to add in something a little bit different. And what you'll notice when you take a look at G is that we've affected the angle. Previously, all the other problems we dealt with, when we went through and we dealt with theta, it was always a trig ratio of an angle. That angle was not manipulated in any way. And so what I want to do now is I want to go through and solve this problem. So, a couple things right off the get-go. We can solve this problem any way we like. And for some of us, because we notice that we're talking about cos being equal to 1, then we may want to use our cos curve. So what I'm going to do is I'm going to start off this problem dealing with our cos curve. So if we notice that, then we know that we could end up dealing with our cos graph. And I know that my cos curve starts at the top and falls. So our cos curve is equal to 1. When does that take place? Well, we know that takes place at this location and at this location. However, if we're going to work our way through graphically on this, then there's something that needs to kind of be focused in on. That because you have the 2 attached to that theta, we really don't have our normal cos curve, if we want to think of it that way. If we want to think of this graphically, we really have a horizontal stretch on that cos curve. And so if this cos graph that I drew in blue was supposed to take me down to 2 pi, then because of the 2 in the function, I'm actually going to get a cos graph that is horizontally stretched by a factor of 1/2. And so when I look and I say, well, when does that cos curve hit 1? I actually hit 1 at this spot. However, another wrinkle pops in that because the restriction in the problem is asking us to solve for theta up to 2 pi, you'll notice that my yellow graph isn't sketched up to 2 pi. That I'll actually get another cycle that will fit until I get to 2 pi. That's what's telling me I actually have 3 solutions to this problem. So if I were to answer this problem, then I have my red x's at all the locations where my red or gold curve is equal to 1. And so therefore, my answer for theta would be at 0, pi, or 2 pi. There's my location at 0. Horizontally stretched by a factor of 1/2 puts that one existing at pi, and 2 pi. Now, one of the issues becomes, if we want to think about this problem graphically all the time, and we want to view it as the transformation of those curves, then solving some of these trig equations can be lengthy. Think about the time that you had to invest to go through to create the equation of a transformed curve. We may not want to tackle that. So we have another means to be able to solve a problem like this, but I want to keep that graphical solution up so that we can have a sense of why what we're about to do applies. Okay, what I want to focus in on is the blue graph that I have up above. I'm just going to draw on a new set of axes. And if we can think of one key concept, the graph is a coast graph, and you know your coast curve does this. We should all have that in our back pocket. Then one big idea comes into play. Anytime I affect the angle, and notice it's an affect, I'm affecting the angle, then I have to affect the domain. So if we look back up in the original equation, you'll notice underlined in blue, we doubled the angle. And as soon as I see doubling the angle, then I have to double my domain. So my old domain was 0 to 2 pi. My domain on double theta then would be doubling 0 and doubling 2 pi. This is the restriction that I actually want to work with for 2 theta. And so if we come back down here and notice on our graph, I have only sketched that curve or considered that curve up to 2 pi. That what I need to do then is I need to extend that curve out to 4 pi. So I'm just going to get rid of that star. And now if I was to answer that same question, when is my coast curve equal to 1? It's equal to 1 at 0, it's equal to 1 at 2 pi, and it's equal to 1 at 4 pi. That I can just use my basic coast graph to solve this problem. So how do I come up with my solutions then? Well, what I have is that whatever my angle is, which the inside of my coast right now is 2 theta, has solutions at 0, 2 pi, or 4 pi. But notice that those equations that I just built don't solve for theta. They solve for 2 theta. Notice that's what I examined here, that the cos of 2 theta equals 1. Well, now for me to solve for theta, I'm going back to grade 9, and I'm just saying, how do you get rid of a times by 2? Well, we divide by 2. So 0 divided by 2 is 0. 2 pi divided by 2 is pi. And 4 pi divided by 2 is 2 pi. And you'll notice we now have our solutions for theta. I don't know if there's a more important thing that we can discuss right now than what I just circled. That anytime we affect the angle, we have to make sure we affect the domain. And if we have that same effect on our domain when we consider our solutions, then we'll make sure that we have all the solutions we need. Okay, I'm going to argue to us that maybe we've got about 50% understanding. We can maybe see why that action takes place, but we're probably not very confident with it. So what I want to do is I want to jump in and I want to deal with a couple more problems so we can maybe see our way through it a little clearer. Let's kind of deal with a nice nice, easy combination of everything that we've dealt with. So let's take a look at H. We have 2 sine 2 theta minus 1. So we know the first action we want to do is to isolate our trig ratio. That means let's get that sine 2 theta all by itself. So let's get rid of the 1. Let's divide out the 2. Well, now that I have that, I can deal with my rotation angle. My sine is positive, and so therefore, I know that my terminal arm has to be up. I can then drop in my heights, label my triangles, and I can tell with that small opposite side that I'm going to have a small related acute angle. What this now says then is that whatever was on the inside of my angle, 2 theta, that 2 theta puts me in the first quadrant, or whatever was on the inside, 2 theta, puts me in the second quadrant. And what we could deal with then is we can get the theta all by itself, which means we can divide out the 2, or divide out the 2, and we come in on those solutions for theta. I would argue that if we were able to work our way through that, I think we have maybe about 2/3 of what we need on the topic. That I think we're pretty comfortable with the algebra, but we've missed one key idea. If we double the angle, we have to double the domain. Remember, anytime I affect the angle, I must affect the domain. So how does this work in this instance where, I don't want to try to think about what the equation or the graph of 2 sine 2 theta minus 1 would look like. Just keep in mind that what we had was a horizontal stretch by a factor of 1/2. So our curve needs to repeat more. I can ignore everything about my curve if I instead remember, affect the angle, affect the domain. That in fact what I've done is I've missed 2 solutions to this equation. Yes, I found where quadrant 1 could occur and quadrant 2 could occur, but I forgot that anytime I double my angle, I double my domain. And so therefore, I can't just lie in quadrant 1 by just rotating pi by 6. What I need to now deal with is doubling my rotations. Notice that my 2 solutions listed so far would be me rotating one positive direction. But if my original restriction says theta can exist in one rotation, then by doubling the angle, it says that I have to consider 2 rotations. And so maybe what I do is I rotate all the way around and then into quadrant 1, which means that I have another solution for 2 theta. All the way around in pi by 6s would be 12 pi by 6. So to go one more pi by 6 into quadrant 1 puts me at 13 pi by 6. Or for me to go my full rotation means that maybe what I do is I rotate all the way around and then into quadrant 2. And so I would have all the way around, which would be 12 pi by 6, plus the 5 pi by 6 to get into quadrant 2 in the correct position, puts me at 17 pi by 6. So I then have 2 more solutions I can solve by dividing out my 2 and dividing out my 2. There are my 4 solutions to this problem. Okay, a couple things to just make a note of. Notice that all of these solutions do fit your restriction on theta. Theta says 1 full rotation, and I know all of those angle values boxed in purple exist in 1 rotation. Because if I had pi by 12s, then a full rotation would be 24 pi by 12, and I notice that all of those are less than 24. Lastly, when we are solving for double theta, I haven't solved for theta, so it's okay that I happen to have some solutions that are greater than 1 rotation. I'm solving for greater than 1 rotation. So if we can always keep in mind, whenever I affect the angle, I affect the domain, then we're never going to miss any solutions. We can become really fast because we don't have to consider the graph of every function. Okay, let's try another one. Okay, and we take a look at our final problem for today. So what I'm going to do is I'm going to ask you to pause the video, go through and solve this problem, and see if we can match up in the end. Okay, pause the video now. Okay, and we should be back. So for us to go through, this should have been pretty automatic. To say that I'm going to isolate my trig ratio, we could then go through and build our rotation angles. Your tan is negative, so your opposite and adjacent have to be opposite signs. So that means I am to the left and up, or I am to the right and down. We can drop in my opposite. Oops, that would not be negative. My adjacent. That's going to make a pi by 6 related acute angle. And I think that if you got into this instance, where you then said, well, therefore, theta over 2 puts me into quadrant 2, which would be 5 pi by 6, or theta over 2 puts me into quadrant 4, which would be 11 pi by 6, I think you're doing great. We don't forget that now we have to isolate for theta, so that means we have to multiply out our 2. When I multiply out the 2, I'm going to get 10 pi by 6. When I reduce that, I'm then going to get 5 pi by 3. Or when I multiply out my 2, I'm going to get a 22 pi by 6 or an 11 pi by 3. And then I think we're doing really well. Okay, a couple things that you might notice though. We don't have a perfect solution. We're doing really well, but we don't have a perfect solution. Because if we recall back, our restriction on theta was greater than or equal to 0, less than or equal to 2 pi. And if I was to take a look at those two red solutions, that value fits within that restriction. But notice, 11/3 is going to be greater than 2. I cannot accept that solution. I would have to mark that solution as inadmissible. Yes, it is a solution to the equation that makes it be true, but it does not fit our restriction. If we got down to that point, then I think we're doing great. And you actually have a perfect solution. However, I do just want to draw to your attention that I don't think we have exhibited the fullest understanding, because we kind of missed out on a concept about affecting the angle and affecting the domain. There is a better way through this problem, and it's just a way that you can work a little faster. Notice that up in the original problem, that said theta divided by 2. And so inside my ratio, I've divided my angle in half, or I've divided it in 2. I've cut it in half. And if I know that I affect my angle, so therefore I affect my domain, that I'm actually solving for this restriction on theta divided by 2. In other words, if this is one full positive rotation, then this is half a rotation. Which means that's all I have to consider for theta divided by 2. And so therefore, I never even had to worry about quadrants 3 and quadrants 4. So, to step out for just 1 second to this problem, notice in the previous problems, because I had a 2 theta on the inside of my ratio, that meant that I had to consider one rotation and then a second rotation because I doubled my angle. To come back into this problem, because I've taken half my angle, I only have to deal with half of the rotation. Now, you might say, why does that make things better? Well, notice, I would have come up with my full solution then by only examining what was going on in quadrants 1 and 2. That I never would have had to create this equation just to have it give me a value that I would have to deem inadmissible. A, I never had to do that work, but B, I didn't forget to mark it as inadmissible when considering the domain. Okay, let's jump into our last problem for the day. Okay, you can see J up on the screen, and I think we're at a point where we could probably do some good work on this equation. Now, I'm going to give you a little heads up right off the bat. There's a little bit of a quirk to this problem. But what I want you to do is just to work your way through solving it. We're going to put up a solution to see how well we match up. And even though we may match up with an incorrect solution, I still think that it means we're doing good work on this one. So I want you to go ahead, pause the video, and give this one a shot. Okay, pause it now. Okay, we're back. So what I want to do is I just want to kind of work through that problem with what I think you should have pretty comfortably come up with. So I think we should have been fine to say we've got the cos of our angle, and that's equal to my root 3 over 2. I think we then should have been pretty comfortable to say that in this instance, and I'm going to come back to this green in a second, but in this instance, my cos is positive, so I'm off to the right. We should have been pretty comfortable to identify root 3 over 2 as a special triangle. That's going to give me pi by 6 special angles, related acute angles. And so therefore, you would have come up with theta minus pi by 3 gives you pi by 6 in the first quadrant, or gives you 11 pi by 6 in the fourth. Okay, we then go through and we solve. Theta is then going to equal, well, for me to isolate, I need to add. And maybe I'm just doing that in both equations at the same time since it's the same operation. Now we can go ahead, get a common denominator. So in the first case for theta, pi by 3 would be 2 pi by 6. So that's a 3 pi by 6, which reduces to a pi by 2. And then in the second equation, my pi by 3 is 2 pi by 6. So when I add that on, I get 13 pi by 6. I think you're doing decently well if you got to there. Now, I would really hope that since we look at the restriction for today and we see that we can only exist from 0 to 2 pi, that we recognize that 13 pi by 6 is outside the first positive rotation, and therefore it's inadmissible. And I think if you have that solution on your screen, you're doing a great job. And in all seriousness, you have what you need. So what I want to do now is I want to focus on two parts. I want to focus in on the fact that we've affected the angle. And then I want to talk a little bit about the green with my diagram and how me being really casual with my diagram could have an impact on me being able to solve my equation. Okay, let's talk first about the blue. Again, we should be fine that theta has a restriction of 0 to 2 pi. And now, since we're subtracting pi by 3 from our angle, we've affected the angle, we now have to affect the domain. So if I'm going to subtract pi by 3 from theta, then define my new restriction on possible solutions. For theta minus pi by 3, I need to do the same thing. So I need to take my 2 pi and subtract a pi by 3. So that's a 5 pi by 3. And now, the big difference. I also have to change the beginning of my restriction. You'll notice that this is different than the previous two problems, or every problem we've dealt with. Before, I was always multiplying or dividing to my angle, which means if I multiply and divide, to the 0, then there's no change to the beginning of my rotation or restriction. Well, now, because I'm subtracting a pi by 3, that means that my beginning to my angle is no longer 0. It's actually negative pi by 3. Okay, what does that mean for my diagram? Well, if I take a look at my diagram and I just work with the green diagram for now, okay? And again, that's all I'm doing, working with the green diagram. Then for my restriction, my angle actually could go all the way up to 5 pi by 3. And what you'll notice is, for me to rotate around to that terminal arm, I will have gone past my restriction. If I look at my quadrant 4 solution right now, that quadrant 4 solution is an 11 pi by 6. And so for me to rotate using that pink angle, I actually rotated to 11 pi by 6, which is past 5 pi by 3. I'm out of my restriction. And maybe that's why you can see why we get an inadmissible solution for it. Now, you might look at that and you might go, okay, so I would have been able to rule out that solution at the beginning. It really no harm, no foul. And I'm going to say to you, we've missed a solution. But it could be really hard to see it. And so here's where I want to talk about the quality of the diagram we drew in green. You'll notice that I've gotten lazy with my diagrams, and it's a tendency, it's human nature, that when we decide, hey, what quadrant should we be in? Cos is positive. It almost looks like I'm just putting my terminal arms at pi by 4 every time. Like seriously, smack dab in the middle. When it really shouldn't be. And if I do spend a little bit more time to try to be careful with what I'm labeling, then I might be able to see some relationships. So what I'm going to do is I'm going to draw a new diagram. I want to keep my old green diagram. So I'm going to now put down an orange diagram to match the solution that you see. My orange diagram is going to have a set of axes. And now, when I look at my cos being root 3 over 2, we should be quite comfortable to say, if my adjacent side is root 3, then my opposite side is 1, I'm going to have a small angle. So, small angle, small angle. You'll notice that I did not draw my terminal arms in the middle of the quadrant. Why does that help? Well, if that's a pi by 6 related acute angle, then if I have to figure out where my restriction puts me for my possible solutions, I can actually use my diagram to judge if I've rotated too far. Okay, look up at the blue restriction that we have up at the top. And all I'm going to do is I'm just going to erase everything that we wrote just so I can get rid of all the the pink outlines and just get to something that's a little clearer without all the extra writing. There's my restriction on theta minus pi by 3. So what does that say? Well, it says that I start my angles at negative pi by 3. So if I was to put on where my terminal arm would lie, and I'm going to do this in blue to match my restriction, negative pi by 3 is a bigger angle than negative pi by 6. So that blue terminal arm that I just put on would actually be the start, or something that would be allowed within my restriction. Me rotating backwards. So if I look at my blue, that arrow I just put on, shows my negative pi by 3. My blue also shows my positive pi by 3, 5 pi by 3, sorry. Those two blue arrows that you see on your diagram represent the possibilities for my restriction on how I get to my orange terminal arms. Okay, so let's look at that accurate diagram now. Pi by 6 and pi by 3 are now relatively accurate. Let me get rid of my sloppy green diagram. Okay, if I was to look at my diagram, we should be good that I could rotate to positive pi by 6. That little green arrow that I just put on the screen would coincide with what I've just put a green star above in terms of my solution. Nice, that gets us there. I could then rule out, okay? I can rule out me rotating all the way around to 11 pi by 6 because I can see, and I'm just going to zoom in here for a second, that gold arrow rotates too far. I passed my blue arrow. So me getting there by rotating 11 pi by 6 would not fit my restriction. So this whole solution would never show up. Okay, what was the other the other solution that I was alluding to? What I could have on my diagram is another solution, and I'm going to put it with another green arrow. That maybe I rotate negative pi by 6. Notice that me rotating negative pi by 6 fits within my restriction of negative pi by 3. So if I zoom out now, my other solution ends up being my green solution. That theta minus pi by 3 could equal a negative pi by 6. Now again, don't look at that and go, but wait a second. Theta is supposed to be between 0 and 2 pi. Yes, I would agree. Look up at my restrictions in the top right corner. Theta is between 0 and 2 pi. But when I altered my angle, I have to alter my domain. So for theta minus pi by 3, I can have a solution of negative pi by 6. When I then solve for theta, I now need this solution to fit between 0 and 2 pi. And so when I get my common denominator again, pi by 3 is 2 pi by 6, then theta is going to equal a negative 1 plus 2 of them, which is a positive pi by 6. And so if I circle quickly, there are your two solutions for what theta could be, and you will notice that they both fit within 0 and 2 pi. So if I just zoom out a little bit and let you see that solution, I think that problem is one of the toughest ones you'll face. that I think you're going to get quite comfortable by doing practice at multiplying or dividing an angle and affecting the domain. I always think that us going and adding or subtracting something to that angle adds an extra little quirk just because our start is no longer 0. Okay, I hope that solution on J, that's your doozy, went pretty well, and I hope that our discussion on allowing negative angles in this case made some sense. Okay, your job. Jump in, get some practice. I hope it goes well. Good luck.